Example 5e, the system of equations is 2x minus y is equal to negative 8, and the second equation is 2x plus y is equal to 8. Again, we're going to solve this using Gauss-Jordan elimination. So the first thing I'm going to do is write down my initial augmented matrix. Okay, so I have from the first equation, I have a 2 in front of x, a negative 1 in front of y, a negative 8 on the other side of the equal sign. Okay, and then for the second equation, I have a 2 in front of x, positive 1 in front of y, positive 8 on the other side of the equal sign. Okay, all right, so we need to start transforming this. All right, so we're going to start in our first column, and we're going to put a 1 on the principal diagonal, so I need to change that 2 into a 1. Okay, switching two rows doesn't help out here. Probably what you're going to have to end up doing here is dividing this first row by 2. 2 divided by 2 will put the 1 there. Okay, unfortunately, you're going to get a fraction, but sometimes you just can't avoid it. So let's go ahead and take row 1 and divide it by 2, and that's going to become the new row 1. Okay, so your second matrix, okay, we are only changing row 1, so row 2 will stay put. And then we're going to take row 1 here and divide it by 2. Okay, so we're going to end up with 2 divided by 2 is 1, negative 1 divided by 2 is negative 1/2, and then negative 8 divided by 2 is negative 4. Okay, so that's going to be your second matrix. Okay, we do have a fraction, but it is what it is. If you'd rather work with it as negative 0.5, that is fine. Okay, all right, so moving on, we're still in the first column, but now I've got to change the 2 to a 0. Okay, again, getting your zeros, that is best done through the third row operation. Okay, so we are making a change to row 2. So to do that, we need to add to row 2 a multiple of the first row. Okay, so use the 1 that you just got here to do that. Okay, you want to get rid of this 2, so what would cancel that out is a negative 2. Okay, so we're going to take row 1, multiply it by negative 2, that will put a negative 2 right here. So when you add it back to positive 2, you will get your 0. Okay, so this is the row operation you need. Okay, so let's go ahead and do that. Okay, so our third matrix, okay, the first row will stay the same. Okay, so I need to do some work out to the side to get this, okay, the second row. I'll go up here and do it. Okay, so I'm going to do, let's see, I need to do negative 2 times row 1. Okay, that's going to give me, let's see, what is that going to give me? Negative 2. Again, if you're not good with fractions, just do it on the calculator here. Okay, so let's do, let's do negative 2 times negative 1/2. Okay, that's going to give you positive 1. Okay, so negative 2, positive 1, and then negative 2 times negative 4 is positive 8. Okay, we are adding that back to the second row. Okay, the second row is 2, 1, 8. Okay, so add, you're going to get negative 2 plus 2 is 0, 1 plus 1 is 2, 8 plus 8 is 16. So 0, 2, 16 is your new second row. Okay, so that is your third matrix right there. Okay, you're done with the first column. Okay, you've got the 1 on the main diagonal. You zeroed out the rest of the column. Okay, so now we're free to move on to the second column, and we're going to want to put the 1 on the principal diagonal. Okay, so we need to change this 2 into a 1. Okay, the best way to do that, okay, if you look at this row, okay, switching rows is going to undo what you've already done. The best thing to do here is to multiply or divide this row by a non-zero number. Both of these numbers are divisible by 2. Okay, 2 divided by 2 is going to put the 1 right here. Okay, so my next row operation to get the fourth matrix is going to be, I'm going to take row 2 and I'm going to divide it by 2 to get the new row 2. Okay, so that will give me matrix number 4. Okay, so in doing this, I am not changing row 1. Okay, So row 1 is going to stay 1, negative 1/2, negative 4. And then I need to take the second row, which is 0 to 16, and I need to divide each of those numbers by 2. Okay, so 0 to 16, I need to divide each of those by 2. Okay, and that will give me my new second row. Okay, 0 divided by 2 is 0. 2 divided by 2 is 1. Okay, and then 16 divided by 2 is 8. Okay, so that is your fourth matrix. Okay, and it looks like we have one more step to go. Okay, because now that we've got our 1 on our main diagonal, now we need to zero out this negative 1/2. Okay, all right, to get a 0, we've got to apply the third row operation. Okay, we are making a change to row 1. So to row 1, we are going to add a multiple of another row. So the other row is row 2. Okay, what is going to cancel out a negative 1/2? Well, a positive 1/2. Okay, so we are going to do a positive 1/2 times the second row. That would put a positive 1/2 right here. So then when I add it back to row 1, if I add it back to negative 1/2, 1/2 plus negative 1/2 will give me the 0. Okay, so this is going to be my next row operation to get the fifth and final matrix. Okay, so let's see here. If we're making this change, row 2 is going to stay put. And now I'm going to go do my work to get row 1. Okay, so I need to multiply row 2 by 1/2. Okay, so if you're multiplying by 1/2, it's the same thing as dividing by 2. So if we multiply each of these guys by 1/2, I'm going to get 0, 1/2, 4. Okay, add it back to the first row. Okay, add. 0 plus 1 is 1. 1/2 plus negative 1/2 is 0. And then 4 plus negative 4 is 0. So your new first row is 1, 0, 0. Okay, we are done. We got the identity, okay, to the left of the vertical line. Okay, you've got 1s on the principal diagonal. You zeroed out above and below. Okay, so we stop, okay, and then you can either turn this back into a system of equations, okay, which you don't have to. You know that if you have this identity here, the top number is the x value, the bottom number is the y value, okay? So your x value needs to be 0, and your y value needs to be positive 8, and that's going to be the system, the solution to the system. Okay, there is one solution here, okay? So our solution, I'll write it back next to the system. Okay, your x value has to be 0, okay? Your y value has to be positive 8, and that's it. Okay, you can check yourself by plugging in these variable assignments into each equation. Okay, 2 times 0 is 0 minus y, so minus 8. That does give you negative 8, so the first equation checks out. And then check the second equation. 2 times 0 is 0 plus y, so plus 8 equals plus 8. Okay, so that works out. Okay, so hopefully from these 5 examples, you've picked up how to do Gauss-Jordan elimination. Okay, you probably are going to need a lot of practice with it. Okay, so you will have some practice problems on my math lab to do. Okay, when we get to the next section, 4.3, we're still going to do Gauss-Jordan elimination. We're just going to apply it to a bigger system. Okay, the biggest you'll have to do in this class is likely 3 equations and 3 variables. It's still going to be the same process. Okay, it's just going to be a slightly bigger matrix. Okay, but you're always going to work column by column. You're going to, every time you start a column, you secure the 1 on the principal diagonal, and then you use that 1 to zero out the rest of the column using that third row operation. Okay, so it works the same way. Okay. We will do one more example in this section, example 6. We are not actually going to work anything out. I am just going to give you a matrix, a final matrix, okay, and you will have to interpret the solution, okay? So let's go ahead and do that, okay? So here we go. Trying to get you to see all 3 matrices at one time. So we're not going to do Gauss-Jordan elimination here. You're assuming that the Gauss-Jordan elimination has already been done And this is the final matrix you ended up with. Okay, so if you read the directions here in example 6, it says each of the following matrices is in the final matrix form for a system of 2 linear equations in the variables x and y. Write the solution of the system. Okay, you are going to find out as you practice that Gauss-Jordan elimination takes a long time. Okay, it takes a while. There's several steps even for like 2 equations and 2 variables. It takes a lot longer for three equations and 3 variables. Okay, so if you're on a quiz or a test, you know I could give you at most probably one of these. Okay, especially if you have a three equation and 3 variable one. They take a long time. So one of the other ways I could ask you a question, instead of having you do Gauss-Jordan elimination every single time, is to give you a final matrix and see if you can interpret the solution. Okay, so that is something you're going to want to know how to do. Okay, so again, in this example, you're assuming the Gauss-Jordan elimination has been done. Okay, and this is the last matrix you end up with. You need to interpret the solution of the system of equations. And we don't have the system of equations to rely on. Okay, we're just looking at the last matrix. Okay, so here's our matrix in part A. Okay, again, when you look at this left side of the matrix, okay, this is the identity. Okay, so if you can get identity, that means there's exactly one solution to the system. Okay, it's equivalent to having 2 lines that you graph out and they intersect in one single point. Okay, so remember, all you have to do here, there's no work. Okay, if you are able to get the identity, the top number is x and the bottom number is y. Okay, if you would turn this back into a system of equations, it would be 1 times, I'll write it out. It would be 1 times x plus 0 times y is equal to 3. Okay, that's what the first row would tell you. Okay, and the second row would tell you 0 times x plus 1 times y is equal to -5. Okay, you simplify this. The first equation is going to tell you x equals 3. The second equation is going to tell you y equals -5. Okay, so there you go. Okay, the first matrix represents a system that has exactly one solution. Okay, the x value that works is 3 and the y value is -5. Okay, on to the matrix in part B. Okay, again, you do not have the original system to rely on. Okay, but that original system has been turned into a matrix and that matrix has been operated on. Here's the final matrix. Okay, what you should realize, you should hone in on this last row. Okay, if I interpreted this guy, okay, again, first column, numbers in front of x, second column, numbers in front of y, and then you've got your equal sign and your number. Okay, this is going to tell me that 0 times x plus 0 times y is equal to -9. Okay, and so if I simplify this, 0 times x is 0, 0 times y is 0. You add that, okay, you're going to end up with 0 equals -9. That is a false statement. It doesn't make any sense. Okay, so if you get something that doesn't make any sense, that indicates no solution. Okay, and again, you can start recognizing this from your matrix without even having to do any work. If you've got zeros on the left and something non-zero on the right, no solution. Okay, all right, last matrix in part C. Okay, again, you want to focus on the bottom row because it's all zeros. Okay, if you translated it in the same way we just did part B, okay, 0 times x plus 0 times y is equal to 0. Okay, this time when you simplify, you get 0 equals 0, which is true. Okay, it makes sense. Okay, a row consisting of entirely zeros indicates infinitely many solutions. Okay, your original system, whatever it is, if you were to graph those lines out, they would be the same line. Every point on that line is going to be a solution to the system. Okay, so you are going to have to parameterize. Okay, so to do that, okay, you need to use the first row. Okay, the bottom row of all zeros indicates that there's infinitely many. Okay, you use the top row to parameterize. Okay, if we translated the first row back into equation form, this would be 1 times x plus 5 times y is equal to 10. Okay, simplify this. X plus 5y equals 10. Okay, parameterize. take this equation and solve for one of the variables. It does not matter if you solve for x or for y, okay? X is easier to solve for here, so I'm just going to pick x, but you could certainly solve for y. It's just going to look different, okay? All right, so I'm going to move the 5y over. I'm going to get that x equals negative 5y plus 10, okay? So now I can write down my parameterization, okay? Based on this equation, which variable am I in charge of, okay? I'm in charge of the y, okay? So my y value is going to be the t value, okay? And then if y is t, then x is going to be negative 5 times y, so negative 5 times t plus 10, okay? So that is your parameterization, okay? So you need two things for part C, okay? You need to tell me that there are infinitely many solutions and that the parameterization is negative 5t plus 10t, okay? So there you go. Here's the answer for this one, okay? Again, if you had gotten to this point and you decided to solve for y instead, okay, you can do that. Your parameterization is going to look different. It's probably even going to have a fraction in it, okay, but it's still correct. So don't be concerned about that, okay? All right, so hopefully you can see another way that I can ask you a question where I just give you a final matrix and just have you write down the solution to the system of equations. Okay, so now we're going to move on to section 4.3, and we will now look at systems involving 3 equations and 3 variables. Okay, and we will continue the process of Gauss-Jordan elimination.